In today's episode of Guns, Thugs, G's, and Hoes, we'll investigate the LED. Oops, screwed it up again. This is E's and holes. All right, so the situation is now speed dating. Somebody has gotten the thugs to push all the electrons to the left and some more thugs to push all the holes to the right. Probably the same electric field. We must have set up an electric field that's got these thugs pushing electrons one way and holes the other way. And those two things go opposite directions because a single electric field affects positively charged things different than it affects negatively charged things differently. And let's see. Oh, these holes aren't real. They're just sort of the absence of an electron, but we've made the analogy that they're sort of the same thing. And how do guns come in? Oh yeah, shoot, my gun just turned off. When an electron meets a hole, this is called a recombination region in here. Yeah, it's the same depletion region that you noticed before. But when this electron and this hole combine, they let out a celebratory shot because they just met each other and they're happy. But that is light coming out. So let's see what I'm talking about in this analogy. Now we've got a battery hooked up to a PN junction, and we've got the positive side of the battery here and the negative side of the battery here. So we've got an electric field inside this guy that's pointing that direction. Now that's going to make the holes want to go to the right, and it's going to make the electrons want to go to the left. And so let's follow the path of one such pair. We've got a hole over here that's going to the right, and an electron over here that's going to the left. When they meet each other, hey, they like to get together, and the cool thing is they release some energy. And we'll make the analogy back to the atom, which perhaps you understand best of all. There's freedom here. This is the electron not near the hole, and now we're starting with that circumstance. But the electron meets the hole, and guess what? There's a place for the electron to go. So energy equal to the change in the freedom band level and the bonded band level where the electron and the hole have reunited is the excuse me, the energy of the photon that's going to be released from this junction. So let's get ourselves I always want to do brown photons. What a ridiculous thing. So we're going to have a photon coming out that direction, and of course it depends on the band gap of the structure. Now let me draw you like a typical band gap. You've got something like this, and there are all kinds of cool things going on. It looks like the side of a basketball. But really, you've got energy here and energy here. This is probably the valence band, and that's probably the conduction band. And you've got electrons up here and holes down here. And when they recombine, some energy can be emitted in the form of light. Now, LEDs are all over the place, and I want to talk to you a little bit about them, but let me show you an example first. Here is a battery, and I'm gonna flip the switch. Well, I'll do that first. It's kind of dramatic. Here are the lights, and I'll flip the switch, and you can see that these suckers are lighting up. Now, what I find interesting is we've got a whole bunch of LEDs strung on this line, and I've got only 4.5 volts. And I'll show you what's interesting about this. Unlike traditional Christmas tree lights, I can take one of these out and they won't turn off. And that's because they're not in what? How do you think these suckers are wired? Figure that out. How are these wired? Because I can take one out and none of the others turn off. What about if I take out this one? Oh, still none of the others turn out. And that's turned off. That's the reason that they can power it with just 4.5 volts. In fact, I would argue that every one of these bulbs is probably getting 4.5 volts. So what does that mean? Series or parallel? You figure that out. I have another example, though, of some LED lights because this is becoming rather interesting. We can do home lighting with LEDs now. Whoa, they're all over the place, though. Let me show you something else cool. I got a stereo at home, and I can press the play button from a long distance away. And the cool thing is, inside of here, there's a light that goes on, and that sucker's an LED. Let's see if we can get into this thing. Yeah, no, that didn't work. Yeah, okay, cool. So right there, see that LED, that guy right there? That is an LED, and that is putting out light when I press the button. But the problem is, I can't see that. If you look into your remote control, you won't see anything happening because it's an infrared LED. So that means it's putting out light that you can't see, but guess who can see it? Yeah, your stereo, or whatever else you're controlling with your IR remote. That's what infrared stands for. That's what IR stands for in the infrared remote. this is kind of a cool remote control. It's got an LED here that's in the visible that lights up when I press and make the infrared light go on, so you can know that your batteries aren't dead. Look, my batteries aren't dead because it's, oh man, it's also flashing on a code. Wow, this is really cool. We should talk about digital electronics some other time. It's like on and then off for a long time and on and on and on. It's sort of like Morse code, and it's communicating to the television which button you've pressed. It's not changing the light that's coming out, it's changing when the light's coming out. And now, okay, on to these. This is a home light. It's an old style LED light, and that means that it's just 3 years old maybe. But I'll turn this sucker on so that you can look at what's going on here. We've got a very, very bright light, and I think I see, if I squint, I think I see 6 LEDs in there, and I don't know if you'll be able to get that from the contrast, so maybe I'll put through a piece of paper and you can, nope, that's just diffusing it. Okay. So it's very bright, and they've designed the plastic around it to push the light in various directions. But something's interesting. If I move it back and forth, oh no, that's not interesting. Maybe that's a little interesting. Well, we'll see when we go back through it. And I want to show you also, the company Cree has been making semiconductors in the United States. Good, solid crystal semiconductors in the United States for a long time. And they started making LED bulbs. So here's a nice one from Cree. It's actually much lighter, and it's very new. You can get these at dang, what is it, Home Depot or Lowe's? You pick your favorite, right? You want the ones that are made in the US from Cree. This one's got a lot of different LEDs, and they're pointing sideways, nothing exactly pointing up, but it's glass, and it's very light, and they're getting cheaper all the time. I think they're 10 bucks right now. And just like in Doritos, you can get that version right there. That might be considered the nacho cheese or something, or you can get Cool Ranch. So depending on what color flavor you like, you can win. Now, LED lighting has gotten to the point of 15% efficiency, and that's amazing compared to incandescent lighting, which hovers around 1% efficiency. So you're gonna save a ton of money if you get LED lighting in your house. That is a very good efficiency, and getting better and cheaper all the time. You might think that every time there's a current going through a diode that you'd get emission of light, because you're always going to have recombination of holes and electrons, but you need a direct band gap like this. If one band is over here and the other one's over here, that's an indirect band gap, and traditional silicon for calculations inside like a transistor or something is an indirect band gap. So you have to do funny things to make actually an LED. And there's something, I don't want to scare you, so I'm gonna warn you about this a little bit. You're about to see something very interesting about what's happening when an LED is hooked up to a circuit where the voltage is not constant. So here's voltage, that's velocity. Here's voltage as a function of time. I've got something like this going on, and I'm gonna plug this in so you can just look at how it appears. These are Christmas tree lights that are appearing all over the United States, and they drive me nuts. I go just crazy when I see these things. So that's fine if you're kind of looking at it like that, but now what? Whoa, oh man, that's annoying. And freaking Cadillac and Lexus, nice cars, are putting these things on their brake lights. Now that's cool, it actually makes a lot of sense because LEDs are reasonably expensive to buy, and the nice thing is, if I'm following behind some Cadillac and it looks like this, right, and it's got a wheel here and a wheel here, they've got brake lights, and they don't want to put a whole bunch of extra LEDs in there. Brake lights and tail lights are going to be using the same LEDs. So you've got dim mode and you've got bright mode, and the only difference is in dim mode, these LEDs are not on all the time. But what drives me crazy is I'm following behind some guy and he's not got his brakes on, he's just got his taillights on. If I'm following behind this guy and the lights are dim because they're regular taillights, they're blinking. And every time I move my head sharply to the side while maintaining focus on these lights, and I guess I mean I'm looking over here but still focusing over there. It's kind of hard to do, but you should try this when you're driving. No, try it when someone else is driving. But look at these lights and then look away while continuing to focus on the lights, and you will see that they're blinking. But not when they put their brakes on. When they put their brakes on, they're gonna have them on full time. This is called duty cycle. And duty cycle is something very interesting that we'll see in the next clip. Be warned, you don't have to watch this. I'm a lumberjack and I'm okay. I sleep all night and I work all day.
He's a lumberjack and he's okay. He sleeps all night and he works all day.
On Wednesdays I go shopping. But did you notice the great contrast with the LEDs that are powered by a battery? Consider these. I'm a lumberjack and I'm okay. I sleep all night and I work all day.
He's a lumberjack and he's okay. He sleeps all night and he works all day.
On Wednesdays I go shopping. And in slow motion again, forget about it. In fact, I'm going to ask you to go back and look at that video of the lumberjack swinging around those flashing lights, and I'm going to ask you to figure out two things. I want you to figure out the duty cycle of the lights, and I want you to figure out the critical voltage at which those LEDs turn on. And I want you to prove that I'm in the United States. I've had a lot of accusations, people thinking that I'm operating out of England. It's not true. The United States has a different speed, what I mean is a different frequency of lights. And so you can prove that I'm in the United States, and you can tell me the operating range of voltages of those LEDs. There are 50 in the string, and you can calculate everything else. Good luck. Positive side of the battery here and the negative side of the battery here. So we've got an electric field inside this guy that's pointing that direction. Now that's going to make the holes want to go to the right, and it's going to make the electrons want to go to the left. And so let's follow the path of one such pair. We've got a hole over here that's going to negatively charge things differently. And let's see. Oh, these holes aren't real. They're just sort of the absence of an electron, but we've made the analogy that they're sort of the same thing. And how do guns come in? Oh yeah, shoot, my gun just turned off. When an electron meets a hole, this is called a recombination region in here. Yeah, it's the same depletion region that you noticed before. But when this electron, in today's episode of Guns, Thugs, G's, and Hoes, we'll investigate the LED. Oops, screwed it up again. This is E's and holes. All right, so the situation is now speed dating. Somebody has gotten the thugs to push all the electrons to the left and some more thugs to push all the holes to the right. Probably the same electric field. We must have set up an electric field that's got these thugs pushing electrons one way and holes the other way. And those two things go opposite directions because a single electric field affects positively charged things different than it affects this electron and this hole combine. They let out a celebratory shot because they just met each other and they're happy. But that is light coming out. So let's see what I'm talking about in this analogy. Now we've got a battery hooked up to a PN junction, and we've got the